Bismillahirrahmanirrahim. Assalamu alaikum dear students. I hope you all are fine and in the best conditions of your health. So today we shall discuss structure activity relationships, and that will be continuation of the previous two lectures on structure activity relationship, right? So in the earlier two lectures you have studied that structure activity relationship is actually a mean to modify the structure in order to get the best biological activity, right? So the structure is actually explaining, the structure actually determines the physical and chemical properties of anything, right? So if you change the structure, you change the physical activities, and you can change the chemical properties as well. And since these physical and chemical properties, they are related to the biological activity, so by changing the structure or by modifying the structure, we can modify the biological activity in order to get the best activity with minimum of the side effects. So the main topics we shall discuss today will be we will have a bit of review on the structure activity relationships, then we shall revise the physical properties and the chemical properties which affect the biological activity, and now we shall discuss about the examples of structure activity relationship, and we shall see that how we carry out the structure activity relationships, right? The structure activity relationship is a method to modify the structure in order to get the best biological activity with minimum side effects, right? So in this context you have studied about the term of pharmacophore. So what's a pharmacophore? Pharmacophore is the arrangement of functional groups in a molecule, and that arrangement is actually responsible for the best biological response, right? So when we carry out the structure activity relationship, we study the pharmacophore. Pharmacophore is not only a functional group, it's just the arrangement of functional groups in a molecule, how they are arranged, whether this group should be at meta position or that group should be at para position to that group, right? So we have to study the pharmacophore as well. So in the second lecture you studied about the physical and chemical properties. Among physical properties which affect the biological activity are the solubility, ionization, partition coefficient, right? The pKa values. So all of these, what happens that these physical properties are responsible for a drug molecule to reach the target. If, for example, in case of ionization, we have studied that according to the pH partition theory, that if a molecule, if a drug is unionized, then it's absorbed maximum. But it's possible that if a drug is absorbed inside the body, but if it's unable to pass through the biological membrane because of solubility issues, then it will not be able to show its effect, right? Similarly, if a drug is able to pass through the barrier but it's not able to interact with the receptor, then the drug will not act. So all of these physical properties, the solubility, the partition coefficient, the ionization, etc., all of these determine the biological activity, because these physical properties are responsible for bringing the drug molecule from outside to inside your body, and it's also responsible for absorption of the drug, and it's also responsible for the permittivity of the drug from outside the cell to inside the cell, right? The drug can only show its action once it is inside the cell. So that involves the ionization of the drug, so the ionization should be optimum. That involves the solubility of drug, right? And that involves the partition of the drug. The drug should have some solubility within the aqueous phase, and the drug should also have some solubility profile in the lipid phase or in the non-polar phase as well. Then we studied about the chemical properties. So among chemical properties we studied about the stereoisomerism. We saw that how conformation and the geometrical isomers and the optical isomers, they interact with the receptor differently. So different conformations react differently with different receptors. If one conformation is binding with a certain receptor, the other conformation cannot bind with the same receptor. So you studied about the example of conformation in acetylcholine in that case. And we also studied about the Eason hypothesis, and according to Eason hypothesis, so if an isomer, if an enantiomer is able to form a minimum 3-point fit, then in that case that will be able to bind with the receptor. So if a minimum of 3-point fit cannot be achieved for certain enantiomer, that will be inactive, right? So these were the different physical properties and these were the different chemical properties which studied in the previous lecture, and now in this lecture we shall study about certain examples of structure activity relationships that have been conducted so far. So medicinal chemistry is basically the application of organic chemistry to produce the medicinal or pharmaceutical agents, which we normally call as drugs, right? So these pharmaceutical agents or drugs, they are divided in different categories, and these different categories or these different classes are made up of small organic molecules. So what do we mean by small organic molecules? That means the molecules that have low molecular weight. So in medicinal chemistry we have a basic concept that the structures which are similar, or the compounds, the classes, the drugs that are similar in structure, they have similar properties, right? So it means that if we have two drugs which resemble in structure, say in medicinal chemistry we predict that they will also resemble in their biological properties, right? So again, coming to the structure activity relationship, so the chemical structure, which means we are referring to, that means the molecular geometry, right? That means the stereoisomerism and the conformational isomerism. That also includes the electronic structures or the electronic effects, means the inductive effect, the resonance effects, where we have electronic density is rich and at which position we have deficiency in the electronic density, and it also depends on the crystal structure of a molecule. So biological activity, what we mean by biological activity, it's the expression of beneficial or adverse effect of the drug on the living organism, right? So biological activity will include both the beneficial effect as well as the adverse effect, right? So structure activity relationship started from 1865, right, when first time two scientists, Brown and Fraser, they determined or they found out that structure is actually related to the function, and if you change the structure, the function of a drug also changes, right? So since that discovery, since that finding, so the structure activity relationship is used by medicinal chemists to synthesize new drugs. For example, just see this example. So this is a molecule, and this is one molecule, but different studies have been carried out to determine that if we can remove this functional group or we can modify the functional group, and if we carry out the modification, what are the results of that modification. So starting from this A ring, right, so starting from this methoxy, different studies have found out that presence of this methoxy is necessary because it is responsible for the binding, right? So if we remove this methoxy, the activity of this structure is lost. Then other study shows that presence of this methoxy is not necessary. So you may have a structure in which there is no methoxy here and you still have the activity, right? And again, this methoxy, that's also important for the correct binding, for the correct conformation and activity. So if we remove this methoxy or that methoxy, right, the activity is lost. Then we have this B ring, right? So if we carry out unsaturation here, if we bring out presence of a double bond here, if we bring a double bond here at that position, then this unsaturation increases the activity, right? So you can have a double bond here, and when we have a double bond here, the activity increases. Then if we carry out the ring expansion, right, it's already an 8-membered ring, but if we carry out the ring expansion, if we convert it into a 9-membered ring, then activity is lost. So since activity is lost, we are saying that ring expansion is not permitted. Secondly, this group, this is an amide group, so this amide group can be replaced by other substituents. However, this epimer should not be lost, because if we if we destroy this chiral center, then in that case the activity diminishes. So this presence of this chiral center and presence of this configuration is very necessary for activity, right? So you can have any other group here. Instead of amide, you can have chlorine, you can have bromine, but the important thing is that this chiral center must be retained, right? So next is on C-ring, right? So you can contract this C-ring. So already this is a 7-membered ring, right? So you can reduce this 7-membered ring to a 5-membered ring or a 6-membered ring. So ring contraction is allowed, right? So if you contract the ring, the activity is not lost, the activity stays like that. Next we have a methoxy group here, right? So methoxy, instead of methoxy you can have any other group. You can have a halide here, you can have alkyl group, alkoxy group, amino group here, but the important thing is that this group should not be bulky, right? So on this structure you can see that we have carried out different studies. So these are more than 10 studies which have been summed up together, and all of these studies, they are indicating that which changes we can carry out on this structure so that we get the best activity, right? So you can draw different structure yourself based on these observations. So you can have a structure in which there is no methoxy here. You can have a structure in which we have replaced any other group here. We have reduced the ring size. We have brought up some other substituent here. We have brought about like unsaturation here, right? So you can draw different structures based on these observations, and the structure you have drawn based on these observations, you can actually synthesize them later in the lab and see for the activity and see if the activity has improved or not, right? So coming towards the structure activity relationship, when we do the structure activity relationship, we follow an analog approach, right? So analog approach means that we carry out following changes in a molecule but in a sequential way, right? So we carry out change one by one to see the change in activity. So we can carry out changes in the homologue. So you have studied about the homologous series in the very basic organic chemistry. So suppose we have a methyl group. So instead of methyl group, we can have an ethyl group, and we see that if there is any change in activity by increasing or decreasing the chain length of carbon. In case if you have a 5-membered ring, you can have a 6-membered ring, or you can have a 4-membered ring, and see if there is any change in the activity, right? So this change in activity by changing the homologues, right? This is one approach. You can increase the chain length, or you can increase the ring size, or you can decrease the chain length, or you can decrease the ring size. The second approach which we use in the structure activity relationship is the molecular fragmentation. We can remove certain fragment from a molecule, or we can add certain fragment in a molecule, and we see that by adding or removing certain molecular fragment, what's the activity change, right? The third change which we use in the analog approach is the addition of functional groups. So we can introduce a new functional group into the molecule at different positions, right? So, and by changing the nature of functional group as well as by changing the position of that functional group, the activity changes. So we carry out both changes. So we carry out the change in position of the functional group as well as we change the nature of functional group, and we see that by addition of functional group, what are the changes in the biological activity. Then we have bio-isostatic replacement, right? So this is actually the bio-isostatic replacement. So we know what are bio-isosters. These are the groups that have same activity, right? So if we replace sulfur with oxygen, so the biological activity will be retained. So those groups which are resembling in the electronic configuration, which are resembling in their size, etc. So if we replace those groups with one another, the biological activity is not lost. However, biological activity can be enhanced. So we can carry out these replacement of bio-isosters and see what are the difference in the biological activity. The fifth approach is the change in stereochemistry. For example, if we have a cis isomer, we can instead try for a trans isomer. If we have an R isomer, we can go for an S isomer. Similarly, we can go for the changes in conformation and see which conformation is more suitable for binding with a receptor, right? And the sixth approach, which normally we use in the structure activity relationship, is ionization, right? So maybe a compound is existing in neutral form, we may convert it into the ionized form, and in the ionized form maybe it has better activity. Or maybe you have a drug that is in ionic form and we can convert it into a pure covalent form and see what are the changes in activity, right? So structure activity relationships involve these six approaches. But always remember that these approaches are not applied at once. So firstly, we will try for different changes in the homologues by increasing or decreasing the ring size or the chain length. Second, after the studying of homologues, we will try for molecular fragments. Then we will try for addition of functional groups and bioisosters, or you can check for the changes in stereochemistry, and you can check for the change in ionization and the biological activity. Right, here we will see some examples of each of these approaches, and then we'll see certain specific examples on that case. Molecular fragmentation, right? For example, we have cocaine, and what we do is that we replace this molecular fragment, right? And what we do, we eliminate this molecular fragment and bring a hydrogen here, right? And when we bring a hydrogen here, we get a more potent drug, which is known as tropococaine, right? So this is the example of eliminating or bringing the fragments. You can see the reverse as well. For example, if you had tropococaine and you attach this fragment here, then you will get the cocaine, right? So tropococaine is more active than cocaine itself. So this is example. In this case, we have removed a molecular fragment and brought about a simple group here, right? So this is example of additional functional group, right? So this is tolazoline, right? And what we have done, that in order to improve the biological activity, we have brought another functional group. So the other functional group is another benzene ring, right? So instead of having a benzene ring, we have a naphthyl group here. So having a additional benzene ring here has increased the activity of the benzene ring. So this is an example how we can carry out addition of functional groups. So now we have bio-isostatic replacements, right? So first example is uracil. So here in uracil we have a hydrogen here, right? So here we have a hydrogen, and you know by isosters that fluorine and hydrogen are isosters of each other. So what we do, that we replace this hydrogen with a fluorine to see the activity. And when we convert this uracil into fluorouracil, the activity is enhanced. So this is example of this bio-isoster replacement. Another example, so we have hypoxanthine here. So in the case of hypoxanthine here, so what we do is that we replace this oxygen with sulfur, because oxygen and sulfur, they are bio-isosters of each other, right? So by replacing that, the biological activity is not lost, but biological activity is enhanced, right? So by replacing this oxygen with sulfur, we get 6-mercaptopurine. So this mercaptopurine is much more biologically active than this hypoxanthine. So here we have another example, and here we have examples of stereochemistry. Let me clear that structure. So if you check here that this is pentobarbital, right? And here we have methyl at, if you start numbering from this point, so here we have this methyl at carbon 1, right? So it has biological activity. So while carrying out the structure activity relationship, we change the position of this methyl to that carbon, right? So instead of having methyl here, so we have put the methyl group here. So this change in stereochemistry, this change in isomerism, this is not stereochemistry actually, this is basically the position isomer. This is example of position isomer. So by changing in the position of this methyl group, the biological activity is enhanced. So this amobarbitol is more potent than this pentobarbital. So here is example of change in stereochemistry, right? So here we have changed this optical isomer from one form to another. So we have not changed this fragment at all. We have changed the stereochemistry of just this fragment. So here you can say that here we have this alcohol group below the plane, and here we have alcohol group above the plane, right? So you can just see that this isomer in which this alcoholic group is below the plane, it has tuberculostatic properties. It is effective against tuberculosis. But this other isomer in which this alcoholic group is above the plane, this isomer is responsible for causing blindness, right? So both of these are isomers of ethambutol, right? So this isomer of ethambutol, this is tuberculostatic, but if we convert it into the other isomer of it, other stereoisomer, so this isomer of this ethambutol, this causes blindness, right? So change in stereochemistry, that's important. So here is another approach. So here is approach of ionization, right? So suppose you have this dimethyl sulfonium analog, right? And you see that it's existing in the ionized form, right? It's taken in the form of this iodide salt of this sulfonium. So this is dimethyl sulfonium analog, and what we do is that in order to check whether by converting that into a purely covalent structure, what happens. So what we do is that we remove this methyl group from here, right? So sulfur with two valencies with two covalent bonds, that's neutral. So by removing one of the methyl groups here, what we get is the permanently uncharged sulfide, and this permanently charged uncharged sulfide is more potent than the charged sulfide, right? So these are the different approaches we do in the analog approach, right? So we can change the homologues, we can change the ionization, we can change the stereochemistry, we can introduce any functional group, or we can add or remove any fragment, right? So now we shall study about some case studies of structure activity relationship, and the first one will be the penicillin, right? So we'll see that what modification we can do in the structure of this penicillin, right? So structure of penicillin. So firstly, when we have to do the structure activity relationship, just see what functional groups we are here. So this is an amide group. These are two hydrogens, and those two hydrogens are cis to each other, right? They are in cis stereochemistry. And then we have a sulfur here, right? We have geminal 2-methyl groups here, and then we have a carboxylic group here, and we have a cyclic amide, right? Cyclic amides are known as lactam. This is a lactam here, right? So these are the different groups that are present here. Now let's see what the structure activity relationships predicts. So the structure activity relationship indicates that presence of the sulfur is normally present in all penicillins, however it's not essential. So you can replace sulfur by any of its bioisoster. You can have a CH2 group here, you can have an oxygen here, it doesn't matter. So presence of oxygen or CH2 does not affect the biological activity, but normally in case of penicillin, sulfur is present here, right? Next, this is a thioazolidine ring, right? And that's 5-membered ring with nitrogen, right? So the structure activity relationships indicate that this 5-membered ring should be saturated. There should be no double bond here. So you can have any other groups. In case of methyl, you can have any other group. It doesn't matter. However, the essential thing is that this 5-membered ring should be saturated. So if you bring about any unsaturation in the ring, the biological activity is lost. Then we have here a carboxylic acid group, right? So whenever this penicillin is introduced in the body, it's introduced in the ionized state. So normally we use the sodium salt or the potassium salt. However, if we convert this carboxylic group into ester, or if we convert it into alcoholic functional group, then the activity is lost, right? It means that this carboxylic group should be present here, because if we convert this functional group, if we convert this carboxylic acid group into some other functional group like an ester or an alcohol, then activity is lost, right? So presence of this carboxylic group is very much important here. And this carboxylic group is normally in the form of salt. Why it's in the form of salt? Because this charged carboxylate ion that binds to the binding site, and it specifically binds to lysine, nitrogen of lysine, in the binding site of its enzyme. Its presence of carboxylic group is necessary here, right? Then we have a beta lactam, and this beta lactam is a 4-membered ring, and you know that from basic chemistry that 4-membered rings are highly strained system, right? So this strained ring is very important. Normally it is observed that if there is greater strain in the ring, so there is greater activity. So presence of this 4-membered ring, which is highly strained ring, is responsible for the activity of this penicillin. Furthermore, this system should be bicyclic, right? So this bicyclic system is responsible for the biological activity. So if we remove this fragment of 5-membered ring, the biological activity is lost, and if we remove this fragment of this amide group, then biological activity is lost as well, right? So presence of this this bicyclic system, that is necessary for the biological activity. And if we study the molecular fragmentation, right? So if we add or remove certain fragments, we know that if we remove any of these rings, the biological activity is lost. Now we have this carbonyl group. So this carbonyl group is in the form of amide, right? And since this amide is in the form of a ring, so this carbonyl is highly electronically deficient here, right? So the strained ring is acting for two purposes. Number one, that's increasing the activity. Second, because of the increased angle, right? So this decreased angle between these carbon and carbon. So because of these decreased angles, this carbonyl group is becoming highly deficient. So what happens that actually the nucleophile has to attack here, right? So the penicillin acts when the nucleophilic nitrogen from your receptor that binds with this carbonyl. So the receptor has to attack as a nucleophile on this carbonyl carbon, right? So this carbonyl carbon should be deficient, otherwise the receptor will not be able to attack on it. So this carbonyl is deficient because it's highly strained system, and secondly this nitrogen because of the strain, and secondly it's tertiary, so it's not able to donate the electronic density towards this carbonyl, right? So this nitrogen is tertiary nitrogen, this tertiary amine, so this tertiary amine is not able to donate the electronic density. Secondly, the ring is strained, which is further making this carbonyl highly electronically deficient, right? So it's important that we have this carbonyl as electrophilic. So if we increase the electronic density of the carbonyl, then in that case the activity is lost. Now we have this acyl amino side chain, or this is an amido side chain. So this electron withdrawing group, this amido group, right, that's important. That's important here, right? And however, if we remove that group, the activity of this group is lost. Secondly, these are the two hydrogens, and if you see that these two hydrogens, these are in cis fashion because they are on the same side. So since they are on the same side, they are having cis geometry. This cis geometry is very important for biological activity. If we convert that into trans, then the activity is lost. Similarly, you cannot have any substitution here. You must have a hydrogen here, right? So suppose if we bring any other group, however we retain the cis geometry, but we replace this group with some other group, then activity is lost. So we must have a hydrogen here as well. So this is the structure activity relationship of penicillin. So by means of this activity you can draw different structures, right, by limiting. So you can have any other group in place of sulfur, right? You can have other groups other than these methyl, but you have to retain this carboxylic group here, you have to retain the nitrogen here, you have to retain these hydrogens here, right? You have to retain this carbonyl here, but you can replace this R group, right? So the R group should not be bulky, because if it's bulky then there will be some problem in the binding. So you can change the R groups here, but remember that R groups should not be bulkier, right? So you can draw different structure for the penicillin, and when you draw a different structure for penicillin, so in future when you carry out the synthesis, then you can check for the biological activity of the synthesized penicillin and see if the activity improves or not. So in this way we can carry out the different preparation of different derivatives of penicillin. So now we have another case study of Camptothecin. So Camptothecin was actually discovered by Wall and Wani. They were two scientists in early 60s, right? And this is actually isolated from tree of joy, and this is basically a quinolino alkaloid, and structure is a pentacyclic ring, meaning it has 5 rings in the structure. So let's see the structure of this Camptothecin. So this is a structure of this molecule. So the rings are mentioned as A, B, C, D and E ring. So firstly we'll study about the functional groups here. So we have A ring as an aromatic ring, B is a pyridine ring. So C ring is a 5-membered ring with a nitrogen here, and this nitrogen is tertiary. Then we have a D ring, that's a 6-membered ring, and it's a highly conjugated system with a ketonic group. And then we have an E ring, and E ring is basically a lactone. Cyclic esters are called lactone. So this is a lactone here, and we have a hydroxyl group here, and we have an ethyl group here, right? So let's see that how the structure activity relationship study predict that how which structures are necessary or which structures are not. So the structure activity relationships indicate that number 1, A and D are essential for activity. So you can modify the other rings, but you don't have to modify these D rings. So you don't have to modify the A ring and the D rings, right? You cannot remove those rings, right? They are essential for the biological activity. However, you can modify them. You cannot remove those 2 rings. However, you can modify A ring as well as B ring, right? So if you carry out modification in A ring or B ring, they are well tolerated, means the activity is not lost. So this D ring, this is a pyridone system, because here we have a nitrogen here and we have a conjugated system. So this ring is a pyridone ring. So this ring actually is required for anti-tumor activity. So if we modify that ring by finishing or by destroying the unsaturation, the anti-tumor activity is lost, right? So this D ring is important here. Then if we carry out a saturation here between carbon number 6 and carbon number 7, so if we convert it into a single bond, that decreases the activity. So activity is not lost, but activity is decreased when we carry out the saturation of this double bond here, right? So now we have this this is the lactone structure. So lactone structure is essential for activity, and if we convert this oxygen into sulfur or nitrogen, right, if we carry out the replacement with this by isosters, then activity is lost, right? So we need to have oxygen here. It should be a lactone ring. Lactone ring is necessary for activity. Further, this stereochemistry is necessary for activity. So if you change the stereochemistry, if you bring this hydroxyl below the plane and if you bring this ethyl group above the plane, then activity is lost. So the stereochemistry should remain the same here, right? So it means that E ring should not be changed much. Then if we modify the C ring or the D ring here, right, so that result in loss of cytotoxicity. So if we are using this drug as anti-cancer agent, then it will not be able to be used as anti-cancer agents if you modify structure C and structure D. The stereochemistry at 20 is very important, and it's currently this is S geometry. So you can calculate the geometry. So this group has first preference, this has second, this has third, and this has fourth preference, right? So you just assign the number and calculate the stereochemistry. This is an S geometry. So S stereochemistry is very important because this S isomer is active, but if you convert it into the other isomer, that's R isomer, this R isomer is not active, right? So by means of these observations, now we know that we can carry out different substitutions on ring A. We can carry out different substitutions on ring B, but we have not to destroy this double bond here, right? So we'll see that how we can modify this A ring and B ring, and how we can have the best activity, right? And we don't have to carry out any modification on C ring or D ring, right? So we don't have to change this stereochemistry, and we don't have to change this electron ring as well, right? So we have the option of carrying out modification on ring A and ring B. So there is no other change we can do. So let's see that how modifications on this structure have been made, right? So this is ring A, this is ring B, C, D, and E. So here oxygen is missing actually, so you can put oxygen here, right? So when we carry out the changes in ring A and ring B, so now what we have done is that we have attached a substituent at this position of ring A, right? So with this substituent at ring A, so this molecule become more potent, and when we have an ethyl group here, the activity is also retained and activity is enhanced. So just see that we have not destroyed this double bond, we have not destroyed this structure of this pyridone ring, we have not destroyed this C ring, we have not destroyed this lactone ring. This is not carbonyl group here, right? The lactone, this oxygen is missing again here, so sorry for inconvenience. So just let me put the oxygen here. So we have an oxygen here, that was missing, and we have an oxygen here, right? So this lactone ring should be retained. However, we have decreased the ring size because that was permitted previously in the structure, in the original structure. So this ring was 7-membered ring, however we have decreased ring. So this is homologue approach, we have decreased the ring size, right? So we have not carried out any other change, and in this way, by these modifications, we have got a medicine which is irinotecan. So irinotecan is more potent than the parent medicine. Another approach, so in topotecan, that's another modified structure of that molecule. So we have modified by bringing two substituents here at the ring A. So this is ring A, we have brought about hydroxyl here, and we have brought an alkyl amino group here, right? So this alkyl group amino and this hydroxyl group here, right? So we have carried out these just two modifications, and sorry, there's another change. So actually, so here we have a carbonyl group here, and this is not here, right? So that was a mistake in drawing. Right, so what we have done is that we have brought these two substituents here, and just see in both the examples we have not changed the stereochemistry, because if we change the stereochemistry, in that case the activity will be lost, right? So this is the change we have done so far. So these are the modifications we can do, right? So we have studied that C and D ring. So if we change the modification, so there is lost in activity, so we don't carry out the changes much in the C and D ring only, right? So in these rings, the only positions that are available for modification are C5, C14 and C17, right? So here we have, this is C5, right, C14 and C17 here, right? So we can carry out modifications in these positions here. We can bring about any substituent at 14 position, we can bring about any substituent at C5, right? However, we don't have to carry out much modifications here, right? So it's essential that we have this pyridone structure here, right? It's important that we retain this 5 structure here, and it's important that we have the stereochemistry and this electron system here. Next we have modifications in the E ring, right? So in the E ring, as I mentioned, that presence of the lactone is important. So cyclic esters are known as lactone. If we convert this lactone into lactam, lactam means cyclic amide, so this is cyclic amide. If we convert the lactone into lactam, then activity is lost, right? Similarly, the alpha hydroxy is important for the inhibition of topoisomerase enzyme as well. So we must have a hydroxyl group here. So this stereochemistry is important here. Also the presence of this hydroxyl group is important here, and the presence of lactone ring is important here. So it means that we don't have much options of changing of this E ring. However, we can decrease the size of that ring, as we have done in the previous example. We can reduce this ring size, and by reducing the ring size, the activity increases. However, if we change the oxygen by nitrogen, the activity is lost. So this replacement of oxygen by nitrogen, this is example of bioisosterism. The decrease in ring size, that's example of homologues. Bringing a substituent, example of the changes or addition of functional group here, right? So next we have another case study, and we have case study of Taxol. So Taxol was discovered by Dr. Wall and Dr. Wani again. So it's also named called by the name of paclitaxel, and trade name is Taxol. So it's complex polyoxygenated diterpenoid. So you are studying now the natural products, so you know about what are the diterpenoids, right? So this is basically a complex oxygenated compound, and it was isolated from a plant named as Pacific yew. And since it was discovered in the state of Texas, therefore that is named as Taxol, right? So this is its IUPAC. This is basically a 9310 pentadecane type tetracyclic system, right? The square brackets, we have 4 numbers, so these 4 numbers are indicating that it's 4-membered ring, right? And in this ring we have N-benzoyl beta phenyl isoserine side chain, right? So just see the structure here. So this is the side chain which was mentioned here, that's C13, right? And the C13 we have this beta serine side chain, and you can see that there are lots of hydroxyl. That's why we say that this is polyoxygenated compound here, right? That's a tetracyclic system. You can see here there's a 4-membered ring, then we have 6-membered ring, then we have a large ring of that 9-membered ring, and we have again a 6-membered ring here, right? So the rings are mentioned as ring A, ring B, ring C, and ring D, right? So here we have 4-membered ring, that's an ether linkage. We have 6-membered ring with a hydroxyl. Then we have, this is a trans ring junction, right? So it means that rings are joined through trans, because these groups are trans to each other. One is above the plane, one is below the plane. So this is a trans ring junction. Again we have this ester group here, right? This is phenoxy ester. We have a ketonic group here, and then we have an acetoxy group here, right? Here we have another hydroxyl group here. We have 2 methyls which are geminal. We have a double bond here, and we have a methyl group here. So let's see that which changes are allowed. So what are the studies which indicate that which changes, if done, they improve the activity, or which changes, if done, they result in loss of activity. So let's start from this 4-membered ring, from the D ring, right? This is an oxetane ring. So presence of this oxetane ring is essential. So just remember that if a ring is more strained, it's more active, just like in case of the penicillin, in which we had a 4-membered beta-lactam ring here. So we have an oxetane ring here. Oxetane ring is 4-membered ring. Since it's highly strained, it's highly active. So if we destroy this oxetane ring, if we carry out the ring opening, in that case the activity is lost, right? The presence of this group is essential here, right? So stereochemistry of this group is here. That's very important here, right? It should be retained here. However, in case of this alcohol, we can have an ester group here, we can have an amino group here, right? We can have an amino ester group here. It doesn't matter, but important thing is that the epimer should remain like that, right? So the configuration should remain the same, right? So if we can destroy the configuration, then activity is lost. Secondly, we have a carbonyl group here. So if we reduce this carbonyl group, then the activity is enhanced. So you can have an alcoholic group here as well. So if you have an alcoholic group here, the activity is increased, right? So if we remove the this acetoxy group from here, then activity is lost. Activity decreases if we remove this acetoxy group here, right? So here we have phenyl isoserine side chain. So all of this chain, this complete chain, is necessary for the biological activity here. Specifically, then an acyl group is important here. This aryl group is essential, right? This aryl group is responsible for better activity. Okay, so the activity is reduced if we replace this phenyl with a methyl group here. So in case of this phenyl, if we carry out the replacement with a methyl group here, then activity reduces to 19%, or 19 times the activity is reduced. So we must have a phenyl group here, and it's important that this hydroxyl should not be hydrogen bonded, and this hydroxyl group should be free, right? So when the in vivo and in vitro studies were carried out, so this hydroxyl, if free, that was active in both cases. However, if we had aster, so aster was active only in vivo studies. However, in vitro studies did not show the activity of that aster, right? So now we have this B ring here. So this B ring is divided into two hemispheres, right? So this part here is the southern hemisphere, this lower part, and this upper part is the northern hemisphere, right? So you cannot carry out much modification in the southern hemisphere, right? However, the modifications in the northern hemisphere are allowed. You can carry out the modifications in the northern hemisphere, right? But in the southern hemisphere you don't have much options to carry out the modification, right? So with this structure activity relationship, we now know that we cannot remove this oxidane ring. We can have an ester group or an amino group here, but the important thing is that stereochemistry is important. We can reduce this carbonyl group, right? We cannot remove this acytoxic group. This side chain must be retained, right? So these are the restrictions we have. So other than these restrictions, we can carry out different modifications and see what is the effect on biological activity, right? So this side chain is very important, and this side chain is basically responsible for the biological activity, right? So here this is a hydroxyl group. So if this hydroxyl group here, if you protect that in the form of an ether, or if you convert it into ester, the activity is lost, right? So it's important that you have this hydroxyl free. It should not be in the form of ester. You should not convert it into any ether linkage. You must have a free hydroxyl group here, right? So you have the southern hemisphere and this northern hemisphere. So the only changes we can do in this specific case, we can carry out changes in this hydroxyl group. We can convert it into amino group, or we can convert it into ester group. Other change we can do is that we can convert this carbonyl into its reduced form, right? There is no restriction on these methyl groups. You can have any other group other than that methyl group here. Again, there is no restriction on this hydroxyl group as well. Also, there is no restriction on this acytoxic group here, right? So we can carry out the modifications for which there is no restriction. So by carrying out these modifications, we can see what are the changes in biological activity. So here we have some more examples of structure activity relationships. For time being, let's see that we have this structure activity of morphine. So these are different morphine derivatives, right? So this is simple structure of morphine here. So this is morphine, simple structure of morphine. So morphine is addictive. We want to convert this morphine into some structure which is not addictive, but that's more potent. So morphine is the best painkiller. We want that painkiller property to be retained, but we want this morphine not to be addictive, right? So this is morphine, and the relative potency is 1. We'll just compare the relative potency, and we'll see how the structure changes are affecting that potency and this addictive nature as well. So we convert this morphine into codeine. So by converting into codeine, we convert this phenolic hydroxyl into methoxy group here, right? So what happens that when we convert this hydroxyl into methoxy group here, the relative potency decreases. However, this codeine is still addictive, right? So it means that we must have an hydroxyl here, because if we convert this hydroxyl into something else, then the activity decreases, right? We want this morphine to be painkiller, but we just don't want it to be addictive, right? So codeine is not a suitable option. So instead of converting this hydroxyl into methoxy group, what we do is that we convert both of these hydroxyl into acytoxic groups here, right? So this is diacetyl morphine, and its common name is heroin. So its potency has doubled than morphine, right? Morphine has potency of 1, but heroin has a potency of 2. So its potency is doubled, but the problem remains the same. It's still addictive. So we don't want to make heroin because it's banned, right? So instead of carrying out the acetylation of both of the hydroxyl, what we do is that we convert just this hydroxyl into acetoxy group and we retain this hydroxyl. So this is acetyl morphine. This is 4 times more potent than the morphine, but the problem remains such, it is still addictive, right? So what we do is that we carry out the methylation of this hydroxyl and we retain this hydroxyl, because we know this hydroxyl is important right here. Whenever we have hydroxyl here, the activity is enhanced, right? So we make this hydroxyl, we retain this hydroxyl, and we convert this hydroxyl into a methoxy group here, right? So when we carry out this change, right, you can see this is known as the heterocodine. It's still addictive, but relative potency is 5, right? So potency has increased, but the problem remains that it's still addictive, right? So now instead of carrying out modification on this hydroxyl group here, we switch over and we change in the fragment, right? So what we do is that we remove this 5-membered ring here, and we also remove that 6-membered ring from here, and we see what are the changes in the biological activity, right? So what we have done is that we have removed this ring. Also we have removed this part of the ring as well, right? So what we have got is that we have 2 methyls here, these are 2 methyls here, this ring here that has been destroyed, and rest remains the same, right? So we study the activity. So the relative potency is the same as that of morphine, and the problem is that it's still addictive, right? So we switch over to another strategy. So we carry out modification in this structure, right? So what we do is that we elongate that chain. So this is homologue approach. This is homologue approach, as well as this is the introduction of a function group here. So we have brought a phenyl group here, and also we have extended that chain of methyl into ethyl group. So if you check that this is non-addictive and the relative potency is 4 times that of morphine, right? So we have got our target. So we carry out another modification. So instead of having a phenyl group here, what we do is that we bring this group here, right? So by making of this change, you can see this is still non-addictive, but the relative potency has decreased a lot. So by means of these modifications, so we have changed the modification in the functional group. So we know that by structure activity relationship that this phenoxide group, this phenoxy hydroxyl group is very important. This phenol must be present, because if we convert this phenol group into some other functional group, the potency is lost, right? The presence of this phenoxy group is very important here. Then we must have a tertiary nitrogen here, right? So we can elongate that chain, and by elongation of that chain, what we get best activity. So presence of this 5-membered oxygen is not important. The presence of this 6-membered ring with a double bond is not important here. The important thing is that we must have 2 methyl groups here. So in future, if you want to carry out with these activities, with structure activity relationship of this molecule, you can carry out the chain elongation of these methyl groups. You can bring about different substituents on that phenyl group here. We can bring about different substituents on that aromatic ring here, and we see what is the effect on the activity. Also, we can increase the ring size of this 6-membered ring with a nitrogen, and we'll also modify this ring, which is also a 6-membered ring of the morphine. So by making these changes, we can check for the changes in biological activity for that molecule. Another example of the structure activity relationship here, right? So we have this structure. So the only change we do is that we replace the function group, right? So this is an electron withdrawing group. It has been found that if we replace this electron withdrawing group, this nitro, with some other electron withdrawing group, the activity is enhanced. So this compound is not active, but if we replace this nitro group with this ketonic group, right, so we get active compound. Its name is C2-phenol, and we replace this nitro with this sulfonyl group, then we get thiamphenol, right? So both of these compounds are active. So this is a replacement of functional group by one another. So here we have some other examples of structure activity relationship. So this is Camptothecin analogs, right? So this Camptothecin, which we have studied in the case study as well. So it has been found that just see the modifications in the ring A, because if you remember the permitted changes, we knew that if we change, we bring about modification in the ring A or ring B, we get some potent compound. So this is the ring A, and we have two substituents here. So we have a methyl group here, and we have a fluorine group here, right? And we have a methyl group here and a fluorine group here at carbon 10 and 11. So just see the IC50 value, right? So this is the inhibitory concentration, right? So it means that in order to inhibit something, so you must have a lower value, right? So this inhibitory concentration is 1.52, and if we just make the change, we replace this fluorine with hydrogen, and if we change this methyl group with the hydroxyl group, then just check the IC50 value is 262, right? But just these two changes result in such an increase in IC50 value. Now we have this flavonoids, and here we have a single bond between carbon 2 and carbon 3. Let's see that if we convert this single bond into a double bond, what's the activity? So flame bond, this is the effective concentration. So this effective concentration for 60, and this effective concentration is 24.61, right? In case if there is a single bond here, but if we bring a double bond here, then the EC60 value, that decreases a lot. That's a decrease to 3.99. Then we have another example of retinoids, right? So here we have a trans ring junction of hydrogen and hydroxyl, right? So we see that if we convert this bond into a double bond, so if we carry out the dehydration, if we carry out the removal of water from this molecule, we see what's the activity. So this is the maximal accumulation of metazentron, and this is 92 value. Just see the values here, and we have a double bond here between 6 and 12. Then the maximal metazentron accumulation value, that decreases to 31%. Right, so this is the change in biological activity by just small variation in structure, right? So just like the scientists have carried out these modifications, you can also see and you can also predict that how we can carry out the modifications in the ring and how the biological activity changes. Another example here, so here we have a structure, right? So just see the functional groups here, starting from nitro group here, right? So it has been shown that the replacement of this nitro by amino group or by hydroxyl group or by sulfonyl group or by cyano group, so these substituents replacement result in loss of activity. So you can try for other substituent, you can try for chlorine, you can try for bromine, you can try for other substituent other than these and check for the biological activity. Second, it has been observed that if this position of nitro group is changed to meta or ortho position, then activity is lost. Means this group should be at the para position. So para position is very important for activity. Then this is the benzene ring. It has been found that if we convert this benzene ring to some other ring system, like if we convert this benzene to cyclohexyl or furyl or naphthyl or pyridyl, etc., right, so the activity is lost. It means we must have a phenyl group here, right? So now we have these two groups here. These must be erythro to each other, right? So if the relationship is not erythro, means they must have same configuration. If one is R, other should be R. If other is S, should be S, right? So if we change the configuration, then in that case activity is lost. So these must be erythro to each other, right? So this hydroxyl group, right? So if you replace this hydroxyl group with some other group, or you extend that chain, or you decrease the carbon length, in that case activity is lost. So it means we must have a primary group here. this must be a CH2OH group here, right? So if you decrease this group or you extend that group, then in that case activity is diminished. However, no studies have been found that affect the changes in this group. So what you can do, you can convert this amide group into ester group and see what changes you get in the activity. Also, you can see what changes will be observed if you replace this chlorine with other groups, right? So that's all for the structure activity relationship. I hope you have understood what is meant by the structure activity relationship, what are the different approaches you can carry out the structure activity relationship, either by changes in the homologues, you can increase or decrease the ring size, or you can increase or decrease the size of the chain. You can carry out the addition of a functional group, or you can change the position of the functional group. You can carry out changes in the stereochemistry. You can add or remove certain molecular fragment, or you can make use of bioisosters, right? So all of these changes, all of these approaches can be used for studying of structure activity relationship. So that's all for this lecture. Thank you.